Hey, welcome to your lesson on static electricity. This is the first topic of this unit talking about all kinds of electricity, but we're going to start out by understanding static electricity and what it is and how it works. So at the end of this, hopefully you will be able to distinguish between static and current electricity. We're going to talk more about current electricity later and identify example evidence of each, and then identify electrical conductors and insulators and compare the resistance of different materials to electric flow. And we're actually going to go even further. We're going to talk about as well semiconductors and superconductors with that discussion. So let's talk about static electricity, and probably the greatest demo that we cannot do because we're not in school is to do the Van de Graaff generator, which causes hair to just be so super statically charged. Very fun demo. But here's a video so you can see it in action. So what is static electricity? What is electric charge? Well, an electric charge is a result of an unbalanced amount of positive and negative charges. So when we have something that has a static or an electric charge, then that means that there is an unbalance between positive protons and negative electrons. So I'll remind you from our work in chemistry that within the atom, I have protons and neutrons, and they're in the nucleus. So they're stuck in the nucleus. And then I have electrons, which are in energy levels around the atom. If you remember from chemistry, protons are what tells us what element we have. Neutrons just change the mass and have to do with the stability of the atom. But then electrons are things that can get gained or lost or shared, right, in order to make chemical compounds. Well, when we talk about static electricity, it's due to electrons moving around, moving from one place to another place. And as a result, things no longer have a balance of positive and negative charges. I like to kind of talk about this like shoes, like right shoes and left shoes. Okay, so ideally, you want a balance of left and right shoes for your feet. Yeah? But if you lose a bunch of right shoes, well, now it's unbalanced because you have more left shoes than right shoes. That's a bad state to be in. In the same way, if I have an unbalance between protons and electrons, I have a charge, right? Because basically it's not even, and so it wants to get even by gaining or losing electrons. So really important, again, that we remember protons are positive, P protons, P positive, and electrons are our negative ones. But only electrons are able to move. Protons cannot move, they are stuck in the nucleus. So only electrons can move from one place to another place. An object can develop a charge by friction. When two objects are rubbed together, electrons are transferred from one object to another. So you've seen this when you shuffle around on the carpet, right? And then you can give somebody a shock. That's friction. That's two things rubbing together. And by having things rubbing together, then as a result, we can end up basically giving a shock or having a buildup of charge. Okay. So as soon as we have an unbalance of charge, we have static electricity. Here's a diagram or a picture, the good old doorknob and key giving a static shock. And this is due to buildup of electrons. So because of the friction, electrons are being rubbed off of the carpet and they build up within you. And then as soon as you touch something metal like a doorknob, those electrons move through your hand to the key to the doorknob. So when something is positively charged, that means that it somehow lost electrons. It no longer has as many electrons as it did. If it's negatively charged, it gained electrons. So it has more electrons than it has protons. And again, this is all about the balance. Objects want to have an even number of protons and electrons, so it presents a force on particles to draw them in. This is why we actually have attraction and repulsion between charged objects. And hopefully we can do some either demos or we can do some experiments around that. So this is a diagram kind of showing, hey, we got some atoms here, right? They all have the same number of protons and electrons. I got 5 electrons, 5 protons, 5 electrons, 5 protons. And then a little bit of friction causes an electron to move from one atom to another atom. This happens, though, on a very large scale. And then at the end of the day, we have an unbalance of electrons. So this ends up being positive, right? Positive static charge because it has more protons and electrons. And this ends up being more negative. If you learned a little bit about ions, this might all kind of sound a little bit familiar. And yeah, it's somewhat related to the idea of ions. So law of charges, 3 laws you must have memorized. Number 1, like charges repel. If I have 2 positives, they're going to repel. If I have 2 negatives, they're going to repel. So anything that is the same charge, same type of charge, is going to repel. Opposite charges attract. So a positively charged object will attract a negatively charged object. And the reason why is because when they come together, they can become more balanced. A positive object needs more electrons. A negative object has too many electrons. So if they come together, beautiful amount of electrons between the two, or at least it can become more balanced than it was. And the third thing is charged objects attract neutral objects. So if I have something that has a positive charge, something neutral will be attracted to it. And that's because it's trying to get electrons from that neutral thing. So will it pull that neutral thing out of balance? Yes, but at the end of the day, right, it still will be better than it was. Okay, this is why if you take, for example, a balloon and you get it all staticky on your hair, it will stick to a wall, right? It's because now you have this statically charged balloon and it's going to attract to neutral things. So again, 3 laws of charges, like charges repel, opposite charges attract, and finally, charged objects attract neutral objects. Charge is measured in coulombs, and a coulomb is a lot of electrons. So when we talk about charge, we actually talk about often like a lot of coulombs, but electrons are super, super tiny. And when we talk about current and stuff, we're talking about massive numbers of electrons. So 1 coulomb is 6.242 times 10 to the 18 electrons. So just imagine that 6 with 18 zeros afterwards. It's a lot. It's a lot of electrons. In other words, 6.242 billion electrons in 1 coulomb. But coulomb is the way that we track charge. Otherwise known as a quintillion. There you go. It is about the amount of electrons that goes into a light bulb in 1 second. So your normal light bulb takes 1 coulomb per second. So in your normal light bulb, if you look around the room right now, it is having 1,000,000 trillion electrons go through it every single second. Absolutely insane. And that again shows you how tiny electrons are and how much we're talking about here. So let's talk now about insulators, conductors, semiconductors, and superconductors. So these are terms you need to know, be very familiar with. First of all, when an insulator is rubbed, electrons are donated or removed. So insulators do not like electrons to move through them. So they insulate the transfer of charge. They prevent electrons from moving through. Just like insulation in your house tries to prevent heat from moving through, insulators prevent electrons from going through. So electrons are donated or removed, but they do not move. They stay on the area it was rubbed, because the charge cannot move through this material easily. This property is due to insulators holding their electrons tightly so they cannot move throughout the material. When you make a balloon staticky, balloons are insulators or rubber, right? And you'll notice that the charge actually just stays on the one part of the balloon. It doesn't go through the whole balloon. It stays to whatever side was actually rubbed. And that's because the electrons cannot move around in the balloon. It is an insulator. The electrons are where they are. So insulators do not allow electrons to move easily because they are held very tightly by the insulator itself. In a conductor, the electrons are not tightly held at all. They are more able to move around from place to place. So they can move freely and distribute themselves throughout the conductor however they need. Most non-metals are insulators and metals are normally conductors. So some great examples of conductors: gold, silver, copper, iron, aluminum, all metals, yes? Well, insulators, glass, rubber, oil, plastic, diamond, these are all like molecular compounds that we're looking at here. They're things made out of non-metal elements. Well, these are pure metal elements right here. Okay, and then these are compounds all made of non-metal elements, except for diamond. Diamond is an allotrope of carbon. But conductors allow the electrons to move freely. Semiconductors are really interesting in that they somewhat allow electrons to move through. They have a little bit of conductivity, more than an insulator, but they still hold their electrons pretty tight. So an example of this is silicon with gallium added. Semiconductors, that property of conducting just a little bit is the whole reason why we have transistors and computer chips. By changing the silicon slightly, by doing something called doping it with germanium and arsenic. As a result, we can actually end up having that silicon conduct a little bit, which allows it to act as a switch, turning off or on based on another current going through it, which is really quite neat. And this is the whole basis of computing, is the semiconducting properties of silicon as an element. So in semiconductors, electrons are held more tightly than they are in a conductor, but less tightly than an insulator, and they can move a little bit. And we can manipulate this in order to accomplish amazing things. So here's kind of a diagram showing the difference. So conductor has very little resistance to electricity moving through it. Semiconductors have some, and then insulators have like very, very high resistance. So it's very tough for electrons to move through. This is way past what you need to know, but essentially it has to do with electrons that are trapped and can't move, and then electrons that can move and the energy gap between the two. Not something you need to know though, don't worry about it, but I thought it was a neat diagram. Superconductors allow electrons to move through incredibly freely. They're amazing. They offer almost no resistance to the flow of electrons, and as a result, they do some pretty crazy things. I'm going to show you some videos on that. But the trick with superconductors is they normally require an extremely low temperature, super cold, in order for them to superconduct. So normally, minus 137 degrees Celsius to absolute zero, negative 273 degrees Celsius. This technology is getting better all the time. I'm sure there are some superconductors that can operate at much higher temperatures now. Okay, it's a huge kind of area of research and science and fascinating stuff. But still, good to know that superconductors need very cold conditions. They have some very interesting and bizarre properties and are used in technologies where a minimal resistance to electron flow is needed. This is a picture of a floating superconductor. Crazy stuff. Again, videos. Okay, so altogether, here's what you need to know about the different kinds of materials. We have insulators, conductors, semiconductors, and superconductors. So in insulators, electrons are held tightly, which results in high resistance to electron flow. Electrons cannot move through easily. Conductors, electrons are loosely held, so there's low resistance. They can move from place to place. Okay, well, semiconductors are kind of medium hold, and they have a medium resistance to movement. So they can move with enough current or whatever going through, but not as easy as conductors, or as easy, as conductors, and easier than insulators, somewhere in between. Superconductors, it's free to move, just move anywhere, and there's like no resistance at all to current moving through it. Think about this as insulators are like really overprotective parents of you cannot go out or do anything or see friends ever. Well, conductors are like, yeah, do your thing, you go wherever you want to go. Semiconductors are somewhere in between of like, you can go out sometimes, but not others. And superconductors are just like, you don't have parents. You can just do whatever you want. You are free. Okay. That is it. That is the different materials and how the electrons are held in the resistance. So if something has a charge, how do we balance it out? When an electric discharge shock occurs, electrons are moving from one object to another in an attempt to balance charges. That's what's happening when something is neutralized. They're either moving from an object to get rid of electrons or are coming into an object to make up a shortage. But electrons are moving to where there was more electrons to where there's less. These shocks can be a safety hazard, especially around flammable materials and sensitive electronic equipment. Even watches can reset when exposed to static electricity. People who build PCs know about this, right? Because when you put the components in, you got to make sure that you don't have any static built up first, or you can actually wreck your PC components with just a little shock, which would just be horrible, wrecking your processor that you spent hundreds and hundreds and hundreds on by not discharging first. Really important when it comes to things like gasoline, like gas tankers, that static buildup doesn't happen. And actually, it can even be dangerous having static buildup before filling up your car if you end up having a shock occurring. It's always best to discharge yourself by touching the car before you go ahead and start pumping the gas. But things are built around that to prevent it from happening, which is good. You can ground an object by connecting it to a conductor that is placed in the earth. This allows electrons to flow into or out of the ground to neutralize charge. So think of the ground, the actual ground, as being like this reservoir of electrons. You can either get electrons out or you can put electrons in. And by grounding something, you are allowing electrons to move back and forth. Non-conducting materials can be neutralized using ionizers, which produce positive and negative ions and neutralize the charge on an object. We're not going to talk too much about that. Just know that ionizers are a thing to make sure that you don't have ion or electron buildup. This is kind of neat. Earth belt. This is conductive and keeps the car or truck or whatever grounded, okay, by having a connection to the ground so that electron buildup cannot occur. You can imagine how important this would be to something like a gas tanker, okay, like a truck carrying gas, that it's really important it at all times is grounded so you don't have electron buildup, static buildup that can then ignite a fire. Because the tires are insulators, so very easily you could have electron buildup, right, with the tank itself. Okay, so that's it. Hopefully that makes sense. Have a good rest of your day.